Welcome back to the deep dive, the place where we leave the abstract theory behind and really put on our hard hats.
Yeah.
We are done talking about the elegance of the math. Today we are going inside the industrial machine that, actually manufactures AI competence.
That's right. And it's something we don't talk about enough. We marvel at the sophisticated reasoning from the latest models, but we rarely look at the sheer logistical and, frankly, the hardware complexity involved in getting them there.
It's all about engineering.
It's all engineering necessity. And before we start, I do need to state this explicitly. This entire analysis is custom crafted for the Rooted Layers podcast. AI insights grounded in research.
Right.
It's designed to give you, the listener, a shortcut to understanding all those hidden costs, all the complexity of scaling a tool using AI.
Absolutely. And the audit we're reviewing today, it focuses on the tool orchestra system. It called this whole process issue 2, the factory.
Very fitting name.
It really is. Our mission here is to understand exactly what it takes to transform a foundational LLM into a reliable agent, something that can select, invoke, and correctly use external tools.
We're moving so far beyond just simple RAG, retrieval augmented generation. This is full orchestration, where the model itself is deciding the sequence of actions to take.
And the core question is just how? How do you build and test something that complex?
Well, we've bundled the analysis into 3, I think, really critical areas. They represent the whole factory floor workflow.
Okay, what else?
First, you have the raw material. That's the ToolScale synthetic data pipeline.
The stuff it learns from.
Exactly. Second, quality control. This involves the unique physics of benchmarking these agents. It's not like testing a normal model.
Right.
The factory itself, the massive infrastructure demands, and specifically why you need a cluster of 16 H100s just for stable training.
16? Wow.
Yeah. And if we were to summarize the critical insight from all the source material, the core bottleneck, it's this. It's not compute anymore.
Really? I thought it was always compute.
Well, compute is getting cheaper, relatively speaking. The real constraint on building effective agents is the lack of high-quality, verifiable training data.
You mean logs of how to actually use the tools correctly?
Optimal sequences of tool calls. That data just doesn't exist in the wild. And that gap, that scarcity, forces the engineers to become data manufacturers.
So we're looking at a system built to generate its own verifiable reality.
That's a perfect way to put it.
Okay, let's unpack this then. Let's start with that fundamental data problem. We are heading straight into dive 4, the ToolScale synthetic data pipeline.
So we have to begin with what the audit called the ground truth bottleneck.
Right.
You and I, we're so used to talking about Gen AI having access to just petabytes of data, common crawl, huge code repositories. It seems like data is everywhere. So why on earth does tool use face a crippling scarcity problem?
Because when you look at the raw internet, you find tons and tons of text, right? But what you don't find are these neat sequential records of a cognitive process. You don't see the input query, the thought process, the 5 failed API calls, the 1 successful SQL query, the resulting data, and then the final answer, all, packaged up with a little correctness score. It's just not there.
It's just not there. For a model to learn how to be an agent, to learn the grammar of action, it needs thousands, ideally millions, of verifiable logs of optimal tool use sequences. We call them trajectories. And when we humans interact with the tool, whether it's Google search, private database, a complex API, we just get the result.
Yeah, you see the answer, not the work.
The messy, complex, sequential decision-making process that got us there is rarely logged. And even if it is, it's not verified against any kind of ground truth. It's just noise.
So the data is abundant, but the verifiable trajectory data, the high-quality instructional material, is basically non-existent in the wild at any real scale.
Which forces the shift from gathering to manufacturing.
Right.
And since human labeling of these really complex action sequences is just way too slow and expensive, and trying to learn from noisy, chaotic, wild data is fundamentally unreliable for this specific training task, the Tool Orchestra authors had to create what they call a closed-loop generation process.
A closed loop. So they built a synthetic world where the ground truth is just inherently known.
Exactly. Let's walk through it. It starts with phase 1, environment synthesis.
And they're building the training universe from scratch.
And they leverage the LLM's own ability to generate coherent structure to do it. First comes schema generation.
So what does that mean in practice?
The LLM defines a functional tool structure. For instance, it might just define an entire library management system, SQL database schema. It'll detail out the tables like books, users, borrow records.
And the LLM is doing this just from natural language instructions. It's basically defining the tools that it will then later learn how to use.
That's the genius of it. And then comes content population. The LLM fills that database with thousands of fake, but, and this is the important part, logically consistent rows.
So it's not just random data.
Not at all. It creates fictional users, assigns them fictional borrowing dates, and it ensures referential integrity. So, a user can't borrow a book that doesn't exist in the books table.
That step is critical. It ensures the whole synthetic environment is internally reliable.
It has to be. And then the final part of environment synthesis, tool definition. They generate the necessary Python functions. They can query this synthetic database. These are the literal tools the orchestrator will learn to call.
The brilliance here seems to be the full control. Every single piece of this environment is defined and known by the system.
Exactly. So that sets the stage. Now for phase 2, task synthesis. This is where the magic of scalable verification really happens.
Okay.
They start with what they call forward generation. A sophisticated LLM, let's call it the teacher model, looks at this synthetic database and asks a complex multi-step question that requires tool use.
Give me an example.
Something like, which user who lives in zip code 90210 has borrowed Moby Dick and The Great Gatsby simultaneously?
Okay, wow. That would require what? 2 or 3 different database queries and then some kind of logical intersection of the results? A human would take a few minutes to figure that out, and the trajectory would be messy.
Right, but because the system created the data, it doesn't need any external validation. It immediately performs backward verification.
Meaning?
The system just executes the optimal sequence of SQL queries itself on its own known synthetic database to get the ground truth answer. If that query returns Alice Smith, well, then Alice Smith is the undeniable, automatically verified ground truth for that specific question in that trajectory.
That closed loop is the entire innovation, isn't it?
It is.
The fact that the ground truth is mathematically guaranteed just completely eliminates that slow, expensive human bottleneck.
It's a fundamental breakthrough for scaling agentic training. It's the industrial process that creates the clean, labeled sequences of, input tool call 1, tool output, tool call 2, final answer that reinforcement learning needs to work.
Okay, but now we get to defining success, which has to be messier than just simple text generation. If the model is using tools, there could be multiple different paths to the correct answer. How do they handle that kind of ambiguity?
They realize that very quickly.
Yeah.
Standard supervised learning metrics, like exact match, they're just inappropriate here.
Because it would punish creativity or efficiency.
Totally. Strict exact match punishes variability. If I ask for a list of users, and one query gets in one step while another query takes 3 steps but gets the exact same list, well, both should count as successful trajectories.
So what do they use instead?
Tool Orchestra adapts the pass at K-metric. It's an approach that was originally developed for evaluating code generation models, like OpenAI's Codex.
Right, pass at K. So instead of evaluating the final answer as just a binary right or wrong, they're evaluating the probability of finding a correct path.
A correct path, exactly. They use a pass at 8 criteria during the data generation phase.
Okay, pass at 8. So how does the path filtering actually work?
So they start by instructing a highly capable model, the teacher thinks something like GPT-4, to generate 8 completely distinct solution paths for that complex library query we just talked about. They're looking for diversity in reasoning.
So they have 8 trajectories on the table. What are the rules for curating them? How do they pick which ones to keep?
There are 3 main rules. First, there's a survival filter. If 0 of those 8 paths successfully lead to the correct ground truth answer after executing all the tool calls, they just discard the problem entirely.
So it's deemed too ambiguous or maybe just too broken to be useful for training?
Exactly. Don't teach the model tasks that can't be solved reliably. It's just noise.
Makes sense.
Yep.
What's the second rule?
Second is the efficiency filter. If all 8 paths succeed, they don't keep all 8. They run all of them through a cost function, and they select and keep only the single most efficient path.
The one with the fewest tool calls or the shortest sequence length?
Precisely. They want to instill efficiency from the very start of the training process. They're curating for optimal process, not just an optimal outcome.
That's a really key distinction. Okay, and the third rule?
And third, the reinforcement filter. This is for the middle ground. If some paths succeed and some fail, they keep all the successful paths, and they label them as positive reinforcement samples for the student model.
So it learns resilience. It shows that multiple, non-optimal, but still successful routes can exist.
Exactly. And this entire process, these three filters, generate a data set of optimal and near optimal processes.
That is incredibly robust, but it brings us straight to the big audit concerns about synthetic bias. The inherent trade-off you make when you choose this kind of verifiable ground truth over, real-world complexity. What is the biggest danger they face by manufacturing their data like this?
Well, the primary risk is something called teacher bias. Since the orchestrator is trained entirely on trajectories generated by a strong, but ultimately finite, teacher model, the student orchestrator can never fundamentally exceed the reasoning capabilities of that teacher.
Wait, hang on. If the student model is also an LLM and potentially a better one in the future, why is it capped by the teacher's reasoning? I don't quite get that.
It's because the training data only contains successful examples as defined by the teacher's logic. The student might become dramatically more efficient at executing those specific logic pathways.
It can get faster.
It can get faster, cleaner, cheaper, but it will never discover a novel, superior strategy that the teacher model itself couldn't conceive of. Research from Goodhart and others confirms this. It improves execution style, but the intellectual ceiling is fixed.
So it's like training a student race car driver, but only on the specific routes that were mapped by a specific rally expert.
That's a great analogy.
The student might hit the gas better and corner faster on those routes, but if the terrain changes or a better unknown racing line exists, the student doesn't have the data to discover it independently.
Exactly. The intelligence in the trajectory is a derivative of the teacher's intelligence. And the second risk is just as insidious. Triviality bias. This is a direct consequence of that closed-loop requirement for verifiable ground truth.
You mean it's just easier to ask questions with objective black and white answers than subjective ones?
Far easier. It is simple to generate and verify questions about simple lookups. What is the capital of X? Or find the average salary of employees in Department Y. These yield concise, verifiable tool use trajectories.
Right.
It is exponentially harder to synthesize a verifiable trajectory for complex reasoning tasks, like why did the Roman Empire fall?
That's right.
Or draft a novel proposal for a carbon tax.
Because those complex tasks have ambiguous or multifaceted answers, they defy a single verifiable ground truth result.
Precisely. And because the system requires 100% verifiable ground truth for scalability, it systematically filters out the most valuable, the most complex, ambiguous, and open-ended tasks.
Which means the orchestrator's complex reasoning circuits, its ability to handle messy, real-world ambiguity, might be systematically undertrained.
Undertrained simply because those tasks never made it past the initial data manufacturing filter.
So the ToolScale pipeline, it provides the necessary scale for training, which is great, but it inherently biases the resulting agent toward a highly efficient execution of simple, factual, and verifiable tasks. That's a crucial limitation baked right into the foundation.
It is the cost of manufacturing competence at scale.
That transition takes us perfectly from the raw materials, the data, to the quality control process. Now we need to prove this manufactured competence actually works in a measurable way.
Right.
So we move into Dive 5, benchmarks and evaluation.
And here, we immediately encounter the industrial reality of Goodhart's law.
When a measure becomes a target, it ceases to be a good measure.
Exactly. We've seen this time and time again in AI. Once a benchmark like MMLU is saturated, it stops measuring intelligence and it starts measuring how well the model was trained against MMLU.
And for an orchestrator, we're not just judging text fluency anymore. It's a different game.
It's a completely different game. We are judging state transitions. Did the orchestrator correctly decide which tool to call? Did it pass the correct input parameters? Did it correctly interpret the tool's output and use that data to progress toward the goal? This requires new, very specific tests.
Let's start with the most aggressive one, the one designed specifically to stress that reasoning ceiling we talked about. Humanity's last exam, HLE.
HLE was developed specifically to include questions that require PhD-level domain knowledge. We're talking advanced differential equations, obscure historical synthesis, complex physics problems. It's designed to be unsolvable by a pure LLM on its own.
So, if the tool orchestra model correctly answers a physics question on HLE, does that mean the 8 billion parameter model suddenly mastered quantum mechanics?
That's the subtlety, and it's a great question. No. It measures tool identification, not intrinsic knowledge. The orchestrator doesn't solve the differential equation itself. It correctly identifies that the Wolfram Alpha tool can solve it. It formulates the equation syntactically correctly, and it successfully passes the query to the tool.
So the credit for solving the physics goes to the tool, but the credit for the intelligence and the orchestration goes to the agent.
You got it. Which makes the benchmark score intrinsically dependent on the quality of the external environment.
Yeah, that makes sense.
If the tool suite is robust, if you have a flawless physics solver, the orchestrator's HLE score can be very high, indicating excellent routing intelligence. But if your tool suite is weak or you don't have the right tool, the orchestrator fails that question, regardless of how intelligent its reasoning is.
It highlights that fundamental caveat. The quality of the available tools really limits the orchestrator's theoretical peak performance.
Absolutely.
Okay, next up, let's look at a test of resilience and memory. Frames, the factuality trap.
Frames tests multi-hop factual reasoning and information synthesis. The task often requires the orchestrator to chain several retrieval steps and then perform a calculation.
What's an example task?
Something like, find the population difference between the two European cities where the authors of War and Peace and 100 Years of Solitude were born.
Wow, okay. That's at least 3 retrieval steps, 2 data points, and then 1 final calculation. It sounds like a pure memory and RAG test.
It's more cute than RAG.
Uh-huh.
It's a test of context window management under extreme duress. The orchestrator has to successfully execute tool call A, get the first author's city data, execute tool call B, get the second author's city data, and then hold both of those retrieval results in its limited context window memory to do the final math.
And the real teeth of this benchmark is the failure mode they inject, right? The distractor injection.
This is the critical adversarial test. When the orchestrator calls the tool, say for the population of the first city, the benchmark deliberately returns the correct factual information plus 5,000 tokens of pure, contextually irrelevant noise.
What kind of noise?
SEO spam, recipe lists, boilerplate legal text, just junk.
So the model is tested not just on its ability to retrieve information, but on its ability to filter the signal from a massive amount of irrelevant noise.
Precisely. It tests the robustness of the model's attention mechanism. Can it successfully isolate and retain only the 2 or 3 crucial data points necessary for the final calculation from a flood of 10,000 tokens of noise?
And if the orchestrator fails to filter,
the noise contaminates its internal reasoning, and it leads to a factual error in the final step. It's a measure of attention filtering under a pretty significant adversarial load.
that provides fantastic insight into how these systems would handle real-world search engine results, which are often cluttered with spam and distracting elements.
Which brings us to the third, and I would argue the most relevant benchmark for business utility. Talk to ToolBench, the user proxy.
This is where they try to measure whether the orchestrator actually has business sense.
It formalizes the utility function. It finally asks the question, does the orchestrator understand and adhere to the cost versus accuracy trade-off?
How does it do that?
It does it by simulating users who have different priorities. Some users prioritize cost savings, so they have a low alpha value. Others prioritize correctness at any price, so they have a high alpha.
And the metric itself, the utility score, it formalizes this exchange rate.
It does. It's a weighted sum where the cost component is subtracted from the correctness component. The alpha parameter is essentially the user's risk appetite knob.
So if alpha is near 1, the system should be willing to spend more to be 100% right. If alpha is near 0, the system should prioritize a fast, cheap, good enough answer.
That's the power of the framework. It moves evaluation beyond simple correctness and into the realm of value delivery. But this formalization leads to a major audit concern. The promoted metric, accuracy per dollar.
Why is that misleading? I mean, if I'm maximizing accuracy per dollar, shouldn't I be maximizing my value?
It seems like it, but it's misleading because it's a linear metric operating in a deeply nonlinear world.
Explain that.
Okay, imagine it's a high-stakes task, like medical diagnosis or fraud detection. Let's say achieving 99% accuracy on a system costs you 50 cents per query. That 99% accuracy results in a highly profitable, reliable system worth millions of dollars.
Okay, makes sense.
Now, consider a cheaper system. It achieves 90% accuracy, and it only costs 5 cents per query. On a linear chart of accuracy per dollar, that cheaper system might look mathematically superior.
It's way more efficient on paper.
On paper. But that 10% difference in error rate in a high-stakes setting could lead to catastrophic errors, liability. A system that is essentially unusable. Its real-world value is 0 or even negative.
Ah, I see. The value doesn't scale linearly with accuracy. The jump from 95% to 99% might be worth 100 times more than the jump from 85% to 90%.
Precisely. And by favoring a linear metric like accuracy per dollar, the benchmarks implicitly favor systems that are cheap and moderately accurate, over those that are expensive and perfect.
And that fails to capture the real-world value curve, where high-stakes utility explodes only near that asymptote of 100% correctness.
Exactly.
This entire suite of benchmarks, while clever, seems to test what you'd call peak capability in a static, perfect environment.
That's right.
Which raises the distinction between internal and external validity. What failure modes of the real world do these benchmarks just not simulate at all?
The benchmarks are designed for training coherence, not production chaos. Okay. And there are 3 major real-world failures that are systematically excluded. The first is tool drift.
An API changes its schema without warning.
Exactly. In production, an external service might update its JSON response structure or change a function parameter name dynamically. The orchestrator was trained on the old schema, and because its knowledge is immutable until the next training run.
The tool call just breaks instantly.
Instantly. The benchmark environment is static. Tool drift simply doesn't happen during evaluation. It's a perfect world.
Okay, what's the second one?
The second is the adversarial environment, which goes way beyond the benign noise we saw in frames. We're talking about adversarial tools.
Malicious actors.
In the real world, search engines don't just return benign boilerplate. They return deliberate SEO spam, phishing attempts, or misinformation that is designed to fool the consumer, or in this case, the agent. The current benchmarks don't prepare the orchestrator for malicious data injection at all.
And the third failure mode sounds like a financial horror story?
It is. Infinite loops.
The $10,000 mistake.
As the auditors call it, yeah.
Yeah.
When the benchmarks run, the execution harness strictly cuts off the orchestrator after knowledge turns, let's say 15 sequential tool calls. This prevents the evaluation from running forever. But in a live production environment,
there is no safety harness?
No. If the orchestrator enters a self-reinforcing loop call tool returns output that triggers a recall, which returns output that triggers the same recall, can create a catastrophic, instantaneous bill.
A live agent could execute thousands of queries in minutes.
And potentially drain an entire budget before a human engineer even notices. The benchmarks completely mask this fundamental operational fragility by simply cutting off the execution.
That makes the impressive benchmark numbers feel very, very brittle. So with this understanding of its manufactured data and its brittle performance envelope, where does the tool orchestra model fit strategically? When should you actually deploy this thing?
Yeah, that's the key question. We have to place it relative to the other architectural choices. And the sources provide a really clear strategic placement based on the trade-off between complexity, reliability, and cost.
Okay, let's look at the 4 major alternatives, starting with the highest reliability option.
That would be the Monolith. Think of it as just using GPT-5 only, for example. It remains the optimal choice for low-volume, high-stakes tasks, especially safety-critical ones.
Wow.
It offers the highest reliability, 99% plus uptime, and the lowest implementation complexity. It's just one API call. The catch is the fixed high cost per query. You use it when you cannot afford an error, but you don't have millions of queries.
Got it. Now, on the other end of the spectrum, what about the deterministic options?
That's the rule-based router tree. This is a hard-coded decision tree. If the input is X, call tool A. If the input is Y, call tool B. It has the lowest cost per query and the highest deterministic reliability because you can audit it and prove it's correct.
So why wouldn't everyone just use a rule-based system? It sounds perfect.
Well, it trades complexity in the operational stage for complexity in the setup stage. It only works if you require absolute interpretability and if your task distribution is completely stable. If the world or your user needs change, your engineers have to rewrite the entire tree by hand.
It's incredibly inflexible.
Totally inflexible.
Yeah.
Which brings us to the middle ground, RAG plus prompted routing.
This is what most people are doing now, right?
It's the fastest path to market. Medium complexity, medium cost. It's ideal for rapid iteration, and when you have known small tool sets, you just prompt the LLM to decide which tool to use.
Oh.
The fragility here, though, is calibration drift.
What's that?
As the base LLM model you're using gets updated slightly by the provider, your meticulously crafted routing prompt might just start failing, and it's incredibly hard to debug why.
Ah, okay. And finally, that brings us to the beast we've been analyzing, the RL-trained orchestrator, tool orchestra.
This has very high implementation complexity. It requires that entire synthetic data factory we just discussed.
Right.
And it has medium reliability due to the system's compound fragility. However,
it offers the lowest long-term query cost.
By far. So the key takeaway is that Tool Orchestra trades a significant amount of operational complexity, requiring a specialized ML engineering team and massive hardware for long-term cost efficiency at extreme scale.
So this is not for the faint of heart.
Absolutely not. The audit concludes that if you are not running at massive high volume, and they specifically target over 75,000 queries per month, the upfront investment in building and maintaining this RL factory simply isn't economically justifiable.
You'd be better off with a monolith or a prompted routing approach.
For sure, it's a high capital path to a low marginal cost.
That economic analysis makes the need for that sophisticated infrastructure suddenly very, very clear. It brings us directly to dive 6, the actual factory machinery.
The training infrastructure.
And why those 16 H100s are not just a luxury, but a mathematical necessity.
16 H100s. That represents an immense investment, and we need to move past the simple idea that they're just needed to make it run faster. Their necessity is rooted in the fundamental statistical instability of reinforcement learning.
What exactly makes RL training so unstable compared to, say, regular fine-tuning?
It's the stability-plasticity dilemma. The agent has to be plastic enough to learn the new, complex tool use policy based on the reward signals it gets. But if the weight updates are too large,
It goes off the rails.
it suffers catastrophic forgetting. It literally loses its core language ability and reverts to generating nonsense. Conversely, if it focuses only on the reward metric, it falls prey to reward hacking, where it generates highly rewarded gibberish that satisfies the metric but is completely useless to the user.
So the hardware isn't just about speed, it's about forcing convergence on this chaotic, high-variance loss landscape without destroying the model's core intelligence.
That's the core technical requirement.
Yeah.
And it stems directly from the variance problem inherent in policy gradient methods, specifically the algorithms used, like GRPO, which is a generalized version of PPO, proximal policy optimization.
Okay, let's try to break down the variance problem with an analogy.
Okay. Think of the model's weights as a ship navigating a soggy ocean. The gradient is the compass telling the ship which direction to turn to reach the reward port.
Makes sense.
In policy gradient methods, that gradient estimate, that compass reading, is calculated by averaging the rewards you observed over a batch of sampled trajectories.
So if the batch size, which you call dollar, is small,
Right?
what happens?
If dollars is small, the compass reading is incredibly noisy and unreliable. You're only sampling a tiny portion of the ocean. The model might, just by random chance, execute one lucky correct answer in that small batch, which gives it a massive reward signal. $3.
And that single lucky rollout then triggers a huge weight update, moving the entire ship dramatically in that one direction.
Exactly. But that update might be statistically wrong for the general population of problems, even though it was right for that one lucky sample. This destabilizes the entire model, causing it to potentially lose its general language competency because it over-indexed on one lucky random event.
So the solution is statistically simple. You just need a massive global batch size.
You must average the gradients over a statistically significant number of rollouts, hundreds or even thousands, to find the statistically true direction of improvement. And that requires accumulating the input data, the forward passes, and the resulting gradients from all 16 H100s simultaneously.
That explains the cluster requirement, and they augment this with a technique called gradient accumulation, right?
Yes, that's a key engineering technique. Gradient accumulation allows the system to run multiple forward and backward passes, calculating all these small individual gradient estimates, and then it aggregates them into one enormous virtual batch before it performs a single large weight update.
Why not just use a physically larger batch size? Why the virtual part?
Because a physically larger batch requires proportional VRAM, the memory on the GPU, to store all the intermediate activations. By accumulating, you virtually increase the statistical batch size for stability without the proportional VRAM cost.
So it's a hack to get around memory limits.
It's essential for robust variance reduction in GRPO when VRAM is the primary constraint on any individual GPU.
That is a very sophisticated solution, balancing stability and hardware constraints. Now let's look at the silent efficiency hacks these clusters enable, starting with context packing or sequence packing.
This relates directly back to the data we discussed. That orchestration data is jagged.
Right.
Trajectories might range from 500 tokens for a simple query to 12,000 tokens for a complex debugging sequence.
So if you pad every single sequence to 12,000 tokens, the maximum context window, you are just calculating attention over thousands and thousands of padding tokens that contain zero information.
You waste a massive amount of compute on padding. Context packing is the solution. You concatenate multiple short, jagged sequences, say trajectory A, trajectory C, and trajectory D, into one long, efficient 12K context window.
You drastically increase throughput, But this introduces a huge engineering vulnerability.
The attention mask.
Explain that.
It is the critical risk. When you pack sequences together, the attention mask must be strictly block diagonal. This means that tokens in trajectory A must only be allowed to attend to other tokens in trajectory A and never, ever to tokens in trajectory C.
And if they do?
If they attend to unrelated tokens, the model is learning to hallucinate based on non-causal or unrelated information.
And if there is just a tiny off-by-one bug in the attention mask implementation, which sounds highly complex,
the model can effectively learn to cheat. It pulls facts from an adjacent, unrelated trajectory to solve its current task, which just destroys the coherence and the statistical integrity of the entire training run. It's an efficiency hack that carries extreme implementation risk.
Okay, let's look at the most restrictive hardware trade-off, the one related to the reference model. Why does simply having this model consume so much VRAM?
So, as we established, the system needs the KL divergence penalty. It's the regularization term that prevents catastrophic forgetting.
The safety brake.
The safety brake. And to compute this penalty, the system needs a frozen, identical copy of the original language model weights available in memory at all times. This copy is the reference model.
And for an 8 billion parameter model, that consumes a significant chunk of an H100's precious VRAM.
It forces a brutal engineering choice. Option 1, offload the reference model to cheaper, slower CPU memory. That saves VRAM. The cost. You create a crippling I/O bottleneck.
So the GPUs just sit there idle, waiting
for data to transfer over the PCIe link, which is relatively slow, around 64 gigabytes. It kills your throughput. So what's option 2?
Option 2, keep it in VRAM.
Right. This maximizes throughput, but it severely limits the available space for the policy model's activations and the batch size, which, as we know, increases gradient variance and instability.
So they have to choose between instability or throughput death. What was Tool Orchestra's solution to break this binary constraint?
They leveraged the power of the cluster. They used FSDP, which stands for Fully Sharded Data Parallel.
Sharding.
Instead of trying to fit everything on 1 or 2 GPUs, they shard or split both the main policy model and the reference model across all 16 H100s.
So sharding reduces the VRAM burden on any single GPU.
It balances the VRAM load while keeping all the necessary data, including the reference model segments, readily accessible. However, sharding introduces a new hard bottleneck, synchronization.
The synchronization has to happen constantly to make sure all 16 segments of the model are updated coherently after every single training step.
And that coordination requires incredibly fast inter-GPU communication, which falls entirely on the NVLink interconnect.
Which is much faster than PCIe.
Much faster, up to 600 GDBs. But when you have 16 GPUs constantly sharding and syncing these massive gradient updates, even that link can saturate.
So the engineering constraint has just moved. It started as a VRAM problem, they solved it with FSDP, and now it's an NVLink saturation problem.
That's right. If the NVLink saturates, the H100s, which are compute monsters, just sit idle, waiting for the synchronization to finish. The entire training run becomes I/O bound. It becomes dependent on the network speed, not the raw computational speed.
That's fascinating.
It reveals that scaling these advanced RL systems is fundamentally a high-speed network engineering challenge as much as it is a machine learning one.
It shows just how many layers of hidden complexity sit beneath the simple promise of an AI agent.
I think. Okay, since we've covered so much ground and dropped some very dense terminology, we should probably consolidate the why it matters for the listener. A quick infrastructure glossary review.
Good idea. Let's start with FSDP. Why did it matter to Tool Orchestra?
It was the necessary technique to split the weights of the massive policy model and the critical reference model across the 16 GPUs, letting them train without exceeding the VRAM limit of any single unit.
NVLink.
The high-speed interconnect. It matters because sharding makes it the ultimate bottleneck. It determines whether your fast compute units spend their time calculating or just waiting for synchronization.
Gradient accumulation.
That's crucial for variance reduction. It virtually increases the statistical batch size, which stabilizes the chaotic policy gradient methods used in RL training. It ensures the model doesn't overcorrect based on lucky random rollouts.
Sequence packing.
The efficiency hack, the one used to concatenate jagged trajectories. It matters because it dramatically increases training throughput by eliminating wasted compute cycles on padding tokens.
Okay, 2 more. KL penalty.
The regularization term. It is the mathematical safety brake that prevents catastrophic forgetting and reward hacking. It ensures the orchestrator retains its core language coherence while it's learning how to use tools.
And finally, the reference model.
The frozen duplicate copy of the policy model required to compute that KL penalty. It matters because its mere presence in the system consumes so much VRAM that it forced all these complex engineering trade-offs regarding sharding and throughput.
This entire deep dive has just been a look inside the engine room.
It really has.
Okay, so let's unpack this and synthesize the key trade-offs. We've seen the sheer industrial scale required, manufacturing perfect data, playing these sophisticated metric games to prove capability, and then using an extreme hardware setup just to overcome inherent RL instability.
The central tension is really that cost efficiency trade-off. Training an RL orchestrator is a massive upfront capital investment in data creation and expertise and in those 16 H100s. And that investment is made entirely to achieve the goal of lower cost and higher efficiency per query later on.
Which makes it a viable long-term architectural choice only for those operating at extremely high volumes. So this means that if you are considering relying on one of these advanced systems, or if you're building one, you now understand that the performance is not magic. It's about overcoming 3 predictable engineering challenges: the synthetic data bias, the metric limitations that favor the merely acceptable over the genuinely perfect, and the gradient variance problem that dictates your entire hardware budget.
You have a shortcut now. A shortcut to understanding the true cost and the inherent fragility that's hidden beneath all the impressive benchmark numbers.
Which leaves us with one final provocative thought for you to chew on. We discussed the limitations imposed by teacher bias, the fact that the orchestrator's reasoning ceiling is capped by the capabilities of the initial model that generated its optimal trajectories.
Right.
So if the orchestrator is merely optimizing the routing and execution of knowledge it was taught, will it ever become a true capability discovery engine? Or is it just stuck being a very efficient follower?
And consider this. What happens when the external tools the model relies on, the APIs, the search engines, the databases, what happens when they evolve faster than the model's complex high-variance RL training loop can adapt?
The competence is manufactured and fixed in time.
But the world it operates in is dynamic. So the final question is, how long does that manufactured competence actually remain relevant?
A fitting point of contemplation as we close out this deep dive into the engine room of modern AI agents. Thank you for joining us for this rigorous look under the hood. We hope you feel significantly more well-informed. We'll see you next time on The Deep Dive.